Okay, then hello everyone to today's seminar on interval methods and control engineering. And it's my very great pleasure to welcome today Nacim de l'Université d'Orléans in France as the very last speaker before Christmas in our seminar series. And yes, Nacim is a very well-known researcher in the area of control engineering, cyberphysical systems, fault-tolerant systems, and yes, also interval observer design. And interval observers, impulsive interval observers, will also be the focus of today's presentation. And without further ado, I'll hand over the microphone to you, Nacim, and the floor will be yours.
Thank you, Andreas. Good morning, good afternoon, everyone. Thank you for joining. It's a pleasure for me to give this talk to this regular series of seminars related to interval methods in general. So I want to talk today about the idea of interval impulsive observers and to try to show you that this framework is quite interesting for robust estimation in a situation where you can have either aperiodic or sporadic sampling and also event-triggered sampling. So I will be presenting essentially the work that has been conducted during the PhD thesis of Ramdani. He was one of my students. Now he's a graduated doctor and hired by a company. And my colleague Nacim, who is associate professor at Grenoble. See how it works. Yeah. So we are considering the framework of cyberphysical systems, where these systems are a typical description of critical infrastructures, because you can have combination of the digital controllers or digital monitoring systems interacting with the actual world. You can have distributed systems in using network or internet in general, relying on cloud computations, for instance, and so on. So this is a quite broad scope of the analysis, and we are these systems are, since they are critical, we need robust methods for either control or estimation, and we also need guarantee certificates for these methods. Essentially, today I will focus about the issue of network controlled system, in the sense that it is a cyber-physical system. I will simplify somehow, where we have a physical system, engineered physical system, and a cyber system where you can have digital components and decision making there. So between the two systems, you have a network that is used, either because the system is distributed or because computation cannot be done on the physical engineered system because they require too much load. So you need to go on the cloud and so on. So what is important here is that you have a network between the physical system and the cyber system. To clarify, maybe we are essentially focusing on feedback controlled systems, and essentially as well in the idea of observers, where we try to reconstruct the state that then can be used in the controller to stabilize the system. So we have a network that is between the sensors and the cyber part, hence the observer. And because of this setting, you can have situations where the network can be either non-reliable. So you have packet loss, you have delays, you have jitter, variation of delays, and so on. And all in all, you will end up with sampling of the measurements that can be used by the observer, sampling which is no longer regular, no longer periodic. And this is called aperiodic or sporadic. From time to time, you have a sampling. This is one case study. And the other situation where you would like to not use the network now is like to reduce network usage and to optimize some performance criteria. That is, you want not to use the network because either it can be costly, it can require more resources than available. Also, the bandwidth can be limited. That is, you cannot you cannot transmit more than a specific amount of data because this is a shared network, for instance. So there are many reasons where you would like to have a sampling that is not simply periodic, but where you would like to control the sampling in a way that you would do sampling only when you need to do so. Of course, this rationale holds for control, where we have seen many researchers, many works that have addressed the issue of event-triggered control, or control using event-triggered control ideas I will explore in the following. And then also this idea of interruption can also be implemented for sensor readings, and this is essentially the talk I will address today. That is, the sensors are either not available or requested upon request, not in a periodic way. Okay, so let me now give some formal statements. So here we have a system that is assumed time continuous but linear, to do things simply. We have, however, a measurement that is discrete time, described by discrete time equation, in the sense that the measurements are not continuously available, but available only at specific time. So TK here. We have additive disturbances. So obviously in the interval method seminar, these, well, not necessarily, but in my talk, they will be bounded, like described by intervals of known bounds. So we are working in a bounded error framework. Now, a periodic sampling is the assumption that the sampling ratio, the sampling rate or the sampling interval between two measurements is not known exactly, but it is between two bounds, so it can vary. But here we assume that it varies within known bounds. Here, note that the data are not necessarily delayed; they are correctly time stamped, but they do not arrive. That they correspond to measurements that are not made at in a periodic manner. Regarding the control sampling, now we would like to tune a performance evaluation here, a performance function, let's say, that would give us the optimal sampling rate. We have to decide this. So I will show you how we can do this. So I will talk about in this talk, then I will introduce or review briefly the idea of robust state estimation, just to map with the interval community and the set membership community. And then I will introduce the framework of interval impulsive observers. And then I will show how we can use this for event-triggered measurement that is controlled sampling, or with uncontrolled sporadic sampling. Okay, so I guess clearly in this series of seminars, the audience have seen a lot of work related to interval observers and set membership estimation using predictor correctors algorithms. But let me just briefly clarify how we managed to why we are studying this kind of work now currently. How did we came to analyze the impulsive systems? So historically, interval estimation with continuous data was assuming that the measurements are available continuously. So clearly, this kind of theory cannot be applied to the case we are working on, that is discrete time sampling and non-periodic sampling. However, these approaches were quite interesting because they used input to state, for instance, theorems, input to state stability theorems, to come with the proofs of stability for the observers, in a way that we have a tuning parameter, observer gain, that can be tuned in a way to ensure practical stability. And then we have a guarantee that the framers we are obtaining, or the enclosures, so you call them as you wish, this maximal and minimal solution that will bound and enclose the actual state of the system, we can have a kind of proof that these the width of these enclosures will not diverge, and we can have a practical stability. So this is very nice, and we would like actually to have this kind of results for situations where you have a continuous time system, but with discrete time measurements and essentially non-periodic measurements. On the other side of the spectrum, you have these set membership predictor corrector approaches where they are by construction they are very easy to use with discrete time measurements, because you can always deal with the forward reachability using standard methods. Either any method can be of interest there, but then you can just use some consistency techniques to filter out feasible sets. So these methods should be easy to implement with a discrete time measurement. However, the difficulty here is that in these predictor corrector approaches, it is very difficult to have a proof of convergence, to ensure the convergence of the sets computed to reconstruct the set. So because there are kind of there is no tuning parameter, so we need to have something that can naturally work with discrete time measurement, but at the same time provide convergence properties and stability theorems and so on. Hence the interval impulsive observer. So an impulsive observer is an idea where you would consider the observer like of course in an abstraction like a new dynamical system from a continuous time system and their discrete time measurements. We can build an observer that is given here in the point version introduced by Ferrante and others in 2016. And the idea is to have a continuous flow here. And then when you have a measurement, to do an impulsive correction, instantaneous correction of the reconstructed state. Here we are in point values. So this is the behavior of a impulsive system. So the dynamical equations that describes the continuous flow are always the same. There is no change in the dynamics. However, we have impulsive change of the state at specific time. The sampling here, you can notice, is not regular, so there is nothing to do. We can have non-periodic sampling there. So this is the idea we have exploited, and the idea is to start from this point observer and to propose a interval version of this impulsive observer, hence the interval impulsive observer framework. To do this, what we need to do is to come with an interval enclosures for these dynamical equations. This we know how to do using internal positive representation or the Müller's theorem or cooperative systems and so on. And here as well, we have algebraic equations, and here we know how to bound them using interval arithmetics or interval methods in general. So for the continuous dynamics, we start by decomposing the A matrix, the matrix that describes the evolution of the system using a Metzler and a negative part. And for the algebraic equation, we have to separate the matrix in positive and negative parts. Doing so, we can now build our interval impulsive observer, and the idea, the spirit is the following. Let's say that at specific time, you have an enclosure of the state you want to reconstruct, and this enclosure here is just considered as a box. So we have the minimal and the maximal solution that are given here. That is this lower bound and this upper bound. Component-wise upper bounds on the set. So using the internal positive realization and the Metzler theorem for the Müller's theorem or cooperativity approach and so on, several methods that are available to do this. You can compute the reachable set over a specific time frame. And this, we have an open loop predictor for the state, okay? And then when the measurement is available, then you would do an impulsive correction. And this correction will emphasize a gain, an observer gain that now we have to tune in a way to ensure that there is a reduction in this set. So that's the main idea of the interval impulsive observer, which in fact generalized the idea of impulsive observers to interval or to sets. So a little more formalism here. Okay, open loop predictor is quite easy to understand. There is nothing else to say. In fact, we have the observer now. The system is no longer a continuous system. This is an impulsive system, like a class of hybrid system that is it shows both continuous evolution for the state, but also discrete jumps. So each time there is a jump, in theory, we are changing the mode. That is, we are not in the same time continuum. So we need to define what we call a hybrid time domain. So it's not enough. It means that it's no longer enough to have a single time subscript here, single time variable, but we need also to know what is the time interval we are in. So it means that between, if you have a continuous flow during this interval domain, then you are in this time interval and this mode. And then if you have a discrete jump, we need to update the number of mode, the index of mode. Okay. Okay, so in the following, I will not use such complicated formalism, but this is the formalism used to properly model the hybrid system, and it is important to understand this. And this also clarifies what we mean by this impulsion, because here is the same time. So this is the state at the same time. This is the state, but this is before the jump, and this is before the jump, and this is after the jump. So I know what it means. Okay, let's go back somehow to something easier. So clearly, by construction and using the classical rationale for interval observers, we can prove that this observer satisfies the framing property, in the sense that if the initial domain are well ordered, if you have an orderings in the initial initial values, initial state for the lower and the upper bound, then this ordering is satisfied all over the time horizon, which is quite important for an observer, is that we always have framing property. So the estimation error is always positive. So then it means that what we have to do is just to analyze the dynamics of the estimation error, that is the error between the actual state, which is unknown, and the bound, the lower bound and the upper bound we are reconstructing. So there is a mistake here, it should be the other way around. So these errors are positive by construction, and then we have dynamics. Well, anyway, the matrices don't bother the matrices, but just the idea is that we have a dynamics where now we have an evolution matrix that involves the sub-matrices of the original system, and this matrix is cooperative, is Metzler, hence we have a positive cooperative system. So we know that by construction, all the errors will be positive. And then in the discrete part, the discrete jump, we have an algebraic equations that shows the positive and the negative part of the correction matrix. So how to ensure that these errors are stable? So what we want to show here, there are several ways to do this. We can work on the width of the enclosure, that is the sum of the two errors, or to analyze each error and to prove that each error stabilizes to zero. Stabilizes at least to a bounded set in the vicinity of zero. Okay, to do this in the work with Jahid, we wanted to explore the tools that have been developed for stability of hybrid systems using the the idea of finite gain LP norms. So first, let me recall maybe some maths here. So based on the work of Nacim in 2013, we have a definition of an LP norm for a hybrid signal. So remember that Z is a signal. We are in hybrid domain defined on hybrid time domains. So this is a hybrid signal in the sense that it shows continuous behavior, and from time to time, it shows discrete jumps. So over a specific time horizon, bounded time horizon, we can define the norm using this equation where you can heap a power of P, power to P here, the square root, the power 1 over P, okay? Which is a square or inverse function of power of P. And then we push towards the maximum time horizon to obtain what we call the LP norm. So sometimes the signals are infinite, sometimes they are finite, because we are in the framework of hybrid systems. So sometimes the signals can be of finite nature. Okay, so then with respect to this LP norm, we can also define the idea of finite gain LP stability. In here, this idea applies to an impulsive system. So an impulsive system is a system where we have a continuous flow in a regular way, like an ordinary differential equation. When the state are in a specific domain. This is called we have a domain that when the set is there, so we know that it flows, and then when the set reaches guard conditions, specific conditions, here you have a jump. You have a jump with a reset function, and then you have an output. So this kind of impulsive systems, this kind of impulsive system is a class of hybrid system. This kind of impulsive systems are finite gain stable, LP stable. If you can find a scalar beta and that satisfies this inequality, and then you have also an idea of the gain between the input and the output being disturbance here and the output being the measurement Y, or the system output Y. And we want now to find a way to prove that a system, or at least a sufficient condition to prove that a system, an impulsive system, is finite gain LP stable. So this is possible if we use the concept of storage function, and these kind of storage functions, if you can find a kind of Lyapunov function that is semi-definite continuously differentiable over the definition domain. And if you can satisfy these inequalities, then you can say that the system, the hybrid system, the impulsive system, this one is LP stable, stable, finite gain LP stable. You can have a look to this kind of equation. I mean, they are very close to what we are usually using with the Lyapunov function and the idea of practical stability. I mean, the ultimate set here is that when you have an equilibrium, this one will be 0, and then you will find something like this. The set will converge towards a ball where the size is essentially driven by these scalars. So hence the gains are related to these scalars. So there is no surprise that we find this kind of equations. And also what we can say is that these kind of equations are stronger than necessary. So these are sufficient equation, but not necessary, because what we are asking here is that we have a continuous flow that is stable and a discrete jumps that is stable as well. But you can imagine situations where continuous flow can be unstable and then the jumps can stabilize, or the other way around. So you can imagine other ways to have stability. But here in this work, we have relied on the definition of the LP storage function by Nacim, and we will be exploiting these ideas. Okay. And then if we manage to find a LP storage function, we have a LP gain stability, and we have an upper bound of the connection between the disturbance and the output, and the gain is upper bound by this value, which is something that relates only to the gains of each evolution, related to age evolution. Okay, let me see now how we can use this to design a interval impulsive observer with an event-triggered mechanism. So, event-triggered mechanism, and more precisely here, self-triggered mechanism, is the idea that we will have an observer that will request measurements only when needed. So here we have the errors, the estimation errors. Sorry, the equations are later and there is no more room on the slide. But this is the observation errors, and we want to push these errors to 0, essentially. What we want to do is to tune the gain L matrix. This is a matrix. We want to gain this L matrix to tune it in a way to ensure LP gain stability. But also we want at the same time have a co-design of the gain and the event-triggered mechanism, in the sense that we can let the gain and the beta scalar just to be tuned. Obviously, there is a connection between the two. Here, if you have a very large beta, it means you allow very large errors on your observer before requesting the measurements. How to tune these to ensure stability? Let me see how we can do that. So we'll come back to these sets later on. But to do this, we explore a set of ideas. The fact that errors are positive, so we are dealing with positive dynamical systems. We use as a storage function, we use a copositive Lyapunov function in the K, which has this form. And we will show, and we find a way to show that we can find a gain L that ensures that this is a storage function, hence we can have LP stability. And then we use also the S procedure, and then we have, of course, worked with P = 1 because of this choice here. And this is the most interesting thing about that, is that we will end up with algebraic inequalities. So the papers are there. There are the references there. You can read them. But what we end up with a verification theorem that gives us an algebraic inequalities that needs to be verified to ensure LP stability. Say you have a matrix, a gain matrix. You want to guess. You guess an L matrix. Then you can ensure stability if you can find scalars. These scalars, including the event-triggered related parameters, that satisfies this inequality. So make sure that this is not in matrix inequalities. This is just standard algebraic inequalities. So you can use them using your favorite solver available in any software, for instance, MATLAB. You don't need to go to complex matrix inequalities. Huh? Okay, so this is one thing that is very interesting about this. So because we are using a copositive linear Lyapunov function, we end up with an algebraic inequality. Of course, these are sufficient conditions, not necessary, but I believe they are easier to solve than a matrix inequality. Okay, so because initially these conditions or this one are the same. These conditions are checks the width of the interval observer. So at initialization, we expect to have a very large width because we don't know where is it. So we use a very large domain. So it is expected that this condition cannot be satisfied at the beginning or during the first time step. So you would need to request the measurement several times at the beginning. And since we are working with an impulsive system, it means you would infinitely many often require measurement instantaneously. So we have a Zeno behavior. To avoid this, to avoid the Zeno behavior, we came up with the idea of a dynamic self-triggered mechanism where the criterion here is kind of degraded at the beginning, and then we have something that would slowly decrease in a way to have more stringent conditions on the observer. That is, we require more precision as we go forward in time. This implies a modification of the storage function, but all in all, we can modify somehow the inequalities, and to include this dynamic event-triggered mechanism where you can see the parameter theta, which was involved here. So hence the corollary. So these inequalities allows you to verify that as a given gain matrix L can ensure stability for your observer, for your event trigger observer, and at the same time you can tune the event trigger mechanism. Okay, but how to tune essentially the gain matrix? So for this, we will suggest a method. But before that, I would like to comment on this idea of the minimal inter-event time. So in this impulsive system, as I was saying a few slides ago, since you do a flow and you have a condition that requests measurements, you may end up in a situation where the contraction that you obtain at the measurement is not strong enough to keep you away from the activation of the condition. Let me try to explain here. For instance, you are the observer is in the flow mode, so you are here, and then you end up in this guard condition. You do a contraction, but then in order to carry on in this flow mode, you need to be sure that to be no longer satisfying these conditions. So we need to prove that the contraction that is made by the observer guarantees that you get enough away from this set. And in this way, we can prove that we have a non-zero minimal inter-event time. That is a bounded minimal inter-event time. But this is very important when we are dealing with impulsive systems. And this, well, we prove that we have a further condition to be satisfied to ensure the existence of this minimum, non-zero, non-trivial minimum inter-event time. Okay, now we need to design this. So to design this, the main issue resides in this matrix, because we need to find a gain L that then enters this matrix identity plus LC, and then you have to decompose positive and the negative values. And this is a nonlinear problem. I mean, you have to do branching, so this is not possible to solve easily with a standard algorithm. So the idea is to do a kind of blossoming technique, what we call a positive realization, in the sense that any matrix can be decomposed in two matrices as a difference between two positive matrices. So the minimal representation would be that the GP here would be this I plus LC plus, and the GN will be the I plus LC minus. But it's okay to let the algorithm just choose random, appropriate matrices, but all in all, the difference of them should give us the correct matrix. So this is a trick that allows us to transform the problem of these nonlinear algebraic equation to a linear, something that can be solved with standard algorithms. Okay. We do this for all the matrices where this problem appears and so on, and then we have new inequalities and so on. So let me move forward. So we can do tuning and we can evaluate. So let me show you some results on a academic example of the double spring mass damper, where we measure position. You can see here the events of the measurement. So this is non-periodic measurement. It's an event-triggered measurement. So we measure the position and we reconstruct the velocities. And maybe more interestingly is the dynamic event triggering conditions. So in green, in blue, you have the width of the observer. So this width here, the sum of these four widths. And in dashed line, you have the threshold that triggers the measurement. So the idea of dynamic triggering is that you start quite large and then you progressively decrease the threshold. So it's you are putting more and more constraints on your observer. And then we can see the observer has reconstruct a set that encloses the actual system, but then you have some over approximation and so on. And then when the width reaches the threshold, then you have a new measurement. And as proved, we have a minimum and intereven time, in the sense that the contraction is strong enough to push away from the guard condition, and hence you need some time in order to go back to this condition. Voila, that's for the event-triggered interval observer. Time is running, but what we have done as well is that we have compared the performance of this observer with the methods from the literature. So there is no, of course, it's the first time an event-triggered mechanism is used with an interval observer, and even more with an interval impulsive observer. So there is no other framework, no other similar work to compare with. However, interval observers, there are many solutions. So approach 1 and 2 approach 1 and 2 assume a continuous time measurement. So of course, they are not similar approach. They use similarity transformation, and a periodic interval observer use discrete time measurement, but use a sample and hold approach. And then you have the event triggered, which is the one I have described. You can see that our approach here are the lower bounds. Our approach is, in general, at least as good as, or even better than the literature. So yeah, we can see here the norm 1 width of the estimate, and then you can see that we are at least as good as the literature, and we require only half the measurement required by aperiodic AO, which we're using discrete time sampling. And of course, you cannot compare with approach 1 and 2 because they assume continuous time measurement. So we are really happy about this, and now we are pushing forward this kind of work in the current work of our group. So let me just briefly show you about the sporadic sampling so that we can leave some time for questions. So in sporadic sampling or aperiodic sampling, the main difference is that we no longer control the sampling, but we know that the sampling will happen. We have a lower bound and an upper bound on the sampling rate. We still want to design an interval impulsive observer. So the main difference with respect to what I have seen previously is that now the impulsive observer includes a timer. So this timer allows us to introduce the idea of jumps. So this timer starts with a non-zero value and corresponds to the sampling rate. So this assumes that we know, in a way, we know when the next sampling will happen. Of course, in reality, you don't know. So you have to wait for the sampling. You can then measure the actual sampling time, and then we can run the next step. But essentially, the theory, we assume we know when the next sample will arrive. So we reset the timer to this maximum value, to this actual value, and then it decreases to 0. When it decreases to 0, then you have a measurement, and then you have an impulsive system. This is an extension of the work that has been done by Ferrante and others in 2016, and we just extended this to interval methods. Here for the synthesis, we used a kind of standard Lyapunov function, although tuned in a way, I mean a quadratic Lyapunov function, but tuned in a way that it has no variation during the flow. In the flow set, it only changes during the discrete jumps, which makes sense because the observer only acts during the jumps, so it makes sense to do this like this. We came with a verification theorem that ends up as a semi-definite programming, because we need to ensure stability for any sampling that is taken between the minimum and the maximum that are known. So this for any sampling rate then leads this semi-definite programming. So it's very difficult to solve. And also the same issues than earlier are still there. Some tricks for the design procedure we came up with. So we still use the positive realization as previously. We also combine projection lemma, polytopic over approximation of interval matrices using Taylor series. And we can reduce the problem to solving BMIs like a finite set of BMIs. So this is a finite number of BMIs, while the problem here was an infinite number of constraints. Okay, so it works more or less. It works on the simple academic system where it works quite well. So here you have an example where you have a measurement that is sporadic. So you can see the sampling is not regular. We measure the first variable, try to reconstruct the second. And then you can have an idea of the sampling that was not regular, and also the evolution of the Lyapunov function, which, although in theory should only change during the measurement, it also changed during the continuous flow. And then when it reaches the kind of limit set here, and since we have practical stability, so it almost never reduced to zero. Voila, concluding remarks. So, okay, I have give you a clue of the framework, interval impulsive observer, and how we can use it for controlled sampling or sporadic sampling. I tried to emphasize the main ideas that we were using in L1 gain approach, and also the issue how to deal with this semi-definite programming and nonlinear matrix inequalities. And I hope you can find this interesting. And here are the two papers that will give you the detail of the theory and the proofs and so on. Thank you very much.
Okay, then many thanks, Nacim, for a very interesting presentation. And yes, I'm pretty sure that there will be some questions. Who wants to start? Carlos, do you want to ask a question, or is this just an applause?
Luc, maybe you want to ask a question.
Yes.
Yes, Luc, then please go ahead.
So thank you for the talk. I wanted to understand. So when you say event triggered, so it's not clear if it is because I have the feeling that sometimes you have some different words, but there is when you say aperiodic sampling, for instance, or self-triggered, or I wanted to know when it is synchronous or asynchronous, or is there a difference between, for instance, aperiodic sampling or asynchronous system? Or is there some difference, or is synonymous?
The idea of synchronous, asynchronous, maybe if you have several systems running on a times with the sampling rate. Maybe if you have several systems running on sampling rates, hence several systems running on periodic sampling of something, maybe the periods are not the same and so on. So this is maybe more related to this idea of synchronisms.
Okay.
But here what we say is that the measurement is usually the opposition here is that periodic sampling. So in periodic sampling, this distance is constant. The difference between tk plus 1 tk is constant, like that would be periodic sampling. Here in aperiodic, we say that this distance, the time between two sampling is not constant. It's not necessarily delayed. I mean the datum arrives on time, but it has been taken on a sampling time which is not periodically chosen. It is somehow different. On this, you can also add some delays, but in this talk, I did not consider delays. So delays for now, I consider there is no delay, which is obviously a strong assumption. But let's say for start that there is no delays. It's just that measurements are not taken on a regular pace.
Yeah. Yes, because in the beginning of your talk, you had you explained something related to a guard condition, which tells you that some event will depend on your state, And here after, I had the feeling that you had not anymore this guard condition.
Okay, so and then the actual system is continuous. So the actual system is not a hybrid system. It's the observer. The observer that we're building is sorry for the slides. The observer has impulsive behavior. So indeed, there is this sampling time can be chosen by a kind of guard condition that is satisfied. In an event-triggered mechanism, this guard condition can be performance criterion to be satisfied or a degradation of performance criterion. But in the impulsive, in the sporadic aperiodic, it's a trick just to have a timer, and when the timer goes to 0, then we say, okay, now we have a measurement. So it's only a modeling trick. It's a modeling thing. It's more relevant. Maybe it is definitely more relevant for this event-triggered mechanism, where we would define a condition that indeed. Sorry, I have to go through all this. Oh God. Anyway, yeah. So, yeah. For instance, or maybe the dynamic one is more relevant. Yeah. So. Yeah, here, for instance, you have a guard condition D when the states, here the error, in fact, enters the guard condition, we trigger a measurement. And this error, in fact, it is checked using the width of the observer. So this is always available. We do not need the actual state. So it's a self-triggered mechanism, because we just compute the quality of the observer, the width of this reconstructed enclosures, and when this width is beyond a performance threshold, then we ignite, we trigger the measurement. Yeah.
Okay. Thank you.
You're welcome.
Okay, further questions? Natalie or Carlos?
Yes, I can start.
Yes, please, Carlos.
Thank you for a really nice talk. I already know a little bit about these articles, of course. Something that I still cannot find, or I cannot understand very well, is something that many times happen in all the event trigger mechanisms. It's about the importance to guarantee non-zero behavior, right?
Yep.
However, we start assuming that we have some tau minimum tau and maximum tau, where it's gonna be all our events. So I mean, the tau, yes, the minimum tau have to be above the Zeno behavior. It doesn't have a sense for me to define one minimum tau that could imply some Zeno behavior.
Maybe it's my bad during the talk. I mean, there are two applications of interval sampling. There are two different things. Either you want to control the sampling, that is, it's a voluntary way you are designing the system in this way, or it's not voluntary and you have a problem. I mean, you have to solve it's a consequence of the system that you have aperiodic sampling. So it's either one of them. So the idea of this non-Zeno behavior is for the controlled sampling. And for the controlled sampling, you do not impose periodicity. Well, of course, you can change the. There is a way to solve problems. I mean, you can always impose a dwelling time here. For instance, instead of just checking the size of the enclosure and decide, you can also have a size plus some timer there. So in a way to ensure. So in this approach of dynamic self-triggered mechanism, there is no condition on the minimal sampling time. So every time this error, this width reaches the threshold, you launch the you trigger the measurement. Let me show the simulation. Yeah, like this.
Yeah.
I don't know. Is it clear?
Yeah, got it. It was the same idea I was thinking. Like, okay, in this case, we are not defining, but we can do it. Yes. So, yes, thank you.
You're welcome.
Okay, do we have further questions? If not, I have at least two questions. Yes, The first one is what you considered so far is when you were looking at your slide number 6, that you have a linear time invariant system where, at least to me, it seems that all your matrices are perfectly known.
Yep.
Do you also have some results on extensions where you have at least uncertain matrices, but let's say the uncertainties are time invariant, they remain constant but bounded?
No, but we can consider this. I mean, I'd be happy to work on this.
Because I think this would be a quite natural extension here, that you assume you have uncertainty in all of your matrices, let's say in A, B, and C, and not only those bounded disturbances that you treated so far as additive terms.
Exactly. Yeah, this would be interesting. We have a paper regarding a switch system with impulsive observer for switch system with periodic measurement. But yeah, it's I mean, it's interesting to work on the extension to certain interval matrices or to switch systems and so on. So this could be interesting indeed.
Yeah,
indeed.
Yes, and my second question is, it's not exactly the same thing that Luc asked before, but I was wondering if it is easy or not to generalize your scenario where you have the, at the moment you're triggering let's say, the impulsive behavior for the complete output vector. You have your,
sorry,
if you mentioned, I'm not sure if you mentioned somewhere the dimension of the output vector, but your output vector y, the measurements will be taken for the complete output vector. And this would be some vector valued sensor. Let's say you have a mechanical system, you're measuring multiple positions, or let's say one position and two velocities or whatever.
Yeah, okay.
And could your triggering strategy also be generalized in such a way that you have several combinations of outputs, that all of them are observable, and you're just triggering a subset of the outputs in order to reduce, for example, the measurement effort, which could again be related to energy consumption in the system?
Yeah, definitely. It's very interesting. Yes, it would be here to disaggregate this, and to have like a matrix, something that allows us to disaggregate, or at least to have a without having
to select the number of output components that are maybe most efficient for reducing the width.
Yeah. Of course, it would be very interesting to do this. Just thinking whether you would need a bunch of observers or only one observer, or Anyway, it's very, very interesting indeed. Indeed, we were focusing on the time. Now we can focus on the components. Indeed. But then, you need some assumptions about observability. You were saying that you would have observability with every component, or you need the whole vector to have observability? It depends.
Yes, I think at least the whole vector must be observable.
Yeah, at least, yeah. But then
it could be possible that you're switching between two combinations or two subsets that are not observable, and at the end you get still a reduction in the width. I think this could be the case.
Yeah, because you can lose observability in one direction, but not the others. And so I can guess if you do some projections on, this is very interesting, actually.
Yes, I think this could be the dual case. Like, for example, you have two unstable dynamic systems, and you're thinking about, for example, reachability or control, that you're switching between two unstable modes, and at the end you end up with a stable one.
Exactly. Okay, so we have found, Andreas, maybe we have found a joint research topic then.
Yes, why not?
So you have to plan for a visit, maybe.
Yes, sure, but definitely after Christmas.
Yeah, I think so.
Okay, but before we are planning trips for research visits, is there anyone else with another question? Okay. No one has raised their hand, or no one has unmuted him or herself. Okay, then, if this is not the case, again, many thanks for your very interesting presentation. Also, many thanks for answering all the questions. And yes, I think, like we just said, there's definitely lots of things to do also for future research into this direction, and a very interesting topic, this impulsive design of interval observers. And yes, to all of you, first of all, have a nice Friday weekend, and yes, definitely also have a nice Christmas time. And yes, hopefully all of you will come well into the new year 2023. And after a short Christmas break or New Year's break, we'll meet again here in the seminar series on the 20th of January. And the first speaker on the 20th of January will be Fabrice Lebas from Insta Bretagne, who will talk about intervals in an underwater robotics context. Okay, see you all of you soon.
Thank you. Bye-bye.
Bye-bye.